Hi, so I'm David Lattimore. For the last year, I've been working on a linker called Wild. So I'll start by giving a high-level overview of what a linker does. I'll talk about some of the interesting things that linkers need to deal with, just a small sample of them. I'll talk about why linking is important to build times. I'll then go over the current status of the linker that I've been writing and some of the optimizations that I've implemented in order to make it as fast as possible. I'll then go over some benchmarks for the current performance of the linker, talk about my plans for future optimizations, my plans for incremental linking and hot code reloading, and then I'll finish by talking about my approach to testing the linker. So at a high level, a linker's job is to take multiple compiler outputs and merge them together into a single executable or shared object. So each of these compiler outputs might be from a different crate or from a different code gen unit within the one crate. Each of these input objects that is passed to the linker is composed of many sections, and these sections can have different types. So some of the sections might be read-only data, some might be read-write data, executable code, zero initialized, read-write data, etc. And there's quite a few different other types. In this diagram here, the boxes are sections, and here each section contains a single executable function. You can have multiple functions per section, but it's advantageous often for the compiler to just put a single function per section, since this allows the linker to eliminate dead code by removing sections that are not referenced. The arrows between the sections here are called relocations, and these are instructions that the compiler emits to request that the linker place a particular value at a particular location within that section when it's written to the output file. So these are things that the compiler cannot know at compile time. For example, it doesn't know where the other functions will go because they're in different sections, and they may not even be in the same compilation unit. There's quite a lot of different kinds of relocations that linkers need to be able to deal with. For example, there are relocations dealing with absolute addresses, relative offsets, as well as other ones that do things like generate an entry in the global offset table, which is a table of pointers. So some of the more interesting kinds of relocations that linkers need to deal with are related to thread local storage. So a thread local is a bit like a global variable, except that you have a separate copy of that variable for each thread in your program. On Linux, there's 4 different access models for how a thread local can be accessed. So there's general dynamic and local dynamic. And if you're writing code that is going to be part of a plugin or might be used by a plugin, then you need to use one of these 2 models. So plugins are like a shared object that will get loaded at runtime to extend your program. So both of these models, general dynamic and local dynamic, require function calls in order to access the thread local. So they're fairly expensive. If your code isn't going to go into a plugin, then you can use faster models such as initial exec and local exec. These are what are called statically allocated. So at program startup, the runtime needs to be able to determine the total size of all statically allocated thread locals. And that means then that it knows the offsets of all of the variables within that space. And that means for statically allocated thread locals, that means space will be allocated for that variable regardless of whether it's ever actually accessed by a particular thread. Local exec can only be used by the main binary for accessing variables that it itself declares, but it has the advantage that it only requires a single instruction in order to access a thread local, so it's very fast. So the linker needs to be able to not only handle the different relocation types for these different thread locals, it also needs to convert between them. So for example, the compiler might pessimistically emit code using the general dynamic access model, and the linker, if it's writing this code into an executable binary, can optionally convert that general dynamic access into a local exec access, thus speeding up your program. Another interesting thing that linkers handle, at least on Linux, is GNU-I funcs. So these are indirect functions. So you have multiple versions of a function, and at runtime, there's a resolver function that gets called. The resolver function's job is to decide which version of the function we want to use. So that the runtime passes to the resolver function information about the current CPU that we're running on, and the resolver function needs to return a pointer to the function that's going to be used. So these ifuncs were used by the recent XZ backdoor, so you may have heard of them. They were used by that because ifunc resolvers get run very early in program startup before certain parts of the program address space have been made read-only. And so the backdoor installed itself by overriding parts of the global offset table during this phase of execution. But more commonly, ifuncs are used to provide faster versions of copies of functions like memcopy. So Rust has a bit of a reputation for having slow build times. I don't know that this is necessarily super deserved. Certainly from my experience, I've had far worse experiences in some of the large C++ code bases I've worked in. But nevertheless, I feel like it could do a lot better. So my ideal for Rust would be if I could make edits to a test in a very large code base with lots of dependencies and see whether that test passes within, say, a few tens of milliseconds. And we're quite away from that at the moment. There's a lot of things that would need to happen for that to be the case, including a bunch of changes that would need to be made to the Rust compiler. But in addition, we would also need to have incremental linking, because linking currently is done, at least on Linux, linking is done from scratch for all of your crates every time you build. And so that's, even if you have a really fast linker, that's still a lot of work. There's a limit as to how fast you can make a linker if you're doing it from scratch every time. So that's why I've chosen to work on incremental linking, and that's what the rest of this talk is about. Well, it's about linking and then incremental linking. So the wild linker the name wild comes from, linkers traditionally end in the letters LD, so GNU Gold, LLD, Mold, and now wild. And the I in wild is incremental, and then the W just made an interesting word. So we ended up with a recursive acronym of wild incremental linker. Wild supports static and dynamic linking. It supports stack unwinding, so if you get a panic, you can see a stack trace, and that requires interaction from the linker in order to generate the frame information that's needed to do stack unwinding. Martin Liska has been contributing to Wild recently and helped out with implementing debug info support. There are also a bunch of features that are somewhat less commonly used that Wild doesn't support. For example, large code models and linker scripts. And Wild is currently x86 64 only and only supports Linux currently. But I would like to expand the support later. I haven't yet started work on incremental linking because I wanted to get Wild to the point where it was working fairly well and had fairly good performance so that I knew what trade-offs I was making as I was implementing incremental linking. But I am getting to the point now where I'm close to doing that. For example, myself and at least one of my friends are using Wild as our everyday linker for all of our development purposes, and it works reasonably well for that. So the linker goes through several phases when it's running. Initially it parses all of the arguments that are passed to it. It then opens all of the files and parses the headers. It then builds a hash map from symbol names to symbol IDs. It then uses this hash map, which is now read-only at this point, to resolve all of the undefined symbols that each object is requesting. And in the process, it determines which archive entries to load. So archives are a bit of an unusual format. They've got a few quirks because they've been around for quite a while. And Rust uses rlibs as its, Rust rlibs that your crates compile to are archive files. So archives are unusual in that objects within an archive are treated differently to objects not in an archive. Specifically, an object in an archive will only be used if it defines at least one symbol that another already loaded object left undefined. And if you get those semantics wrong, then you'll get incorrect program execution, or you can anyway. So some things in the C standard library, for example, depend on archive semantics being implemented correctly. Next, we merge strings. So some of the input sections contain null-terminated strings and can be marked with a merge flag. And that means that the linker needs to go and take this section from all of the input files, find the null terminators, and deduplicate those strings and fix up all the references appropriately. Next, we do a garbage collection phase. So we start from the entry points of the program, such as where the program begins execution and any initializers, and we traverse the graph of all the sections that are referenced. In the process of doing that, we work out how much space we need to allocate to each section, including sections that are generated by the linker. for example, the global offset table. And there's various other sections that the linker generates. Once we know how big each section needs to be, we can assign addresses to all those sections, and then assign symbols to all of the assign addresses to all of the symbols within those sections. At that point, we've completed layout and we know where everything needs to go, and we can start writing the output file. So I've done several optimizations to make the linker run as fast as I can. There's still more work that I can do here, but it's getting reasonably good. One of the most obvious optimizations is running with multiple threads. So in this diagram here, at the top, the blue bar, the blue bar is the main thread of the program, and then the other bars below, the other 8 bars below that are threads in a thread pool. And we can see that for most of the execution of the linker, we're utilizing the thread pool. And then there's a few points in the execution where we drop back to running only on the main thread. In particular, at the end, during shutdown, you can see that we're spending a while running only on the main thread, and I'll come back to that later. Earlier in the execution, there's a few phases where we're building some hash maps and we fall back to a single thread there. I do have some plans to maybe attempt to run those bits multi-threaded. It can be tricky though, because you can easily make it fully multi-threaded, but it's actually slower than when you were doing it single-threaded. So you've got to test your changes carefully there. So another thing Wild does to make it as fast as possible is I mmap all of the inputs and the output. This allows us, so mmap is a way of loading a file into memory without actually reading the bytes necessarily. And so the bytes of the file get read lazily as you access them. And this is advantageous because if you don't access part of a particular input file, then you never actually pay the cost of having that in your address space. It also allows the kernel to do some interesting optimizations, like it can share the memory. Because the memory is read-only, it can share that memory between your process and the system cache. So it reduces overall RAM usage as well. But it does have some costs. In particular, on Linux, it relies on the input files not changing while you're running. So if an input file gets changed, then things will go badly. And that's a responsibility we effectively just have to pass on to the user to say, don't change the input files while the linker is running. So Wild tries as much as possible not to copy data and to just borrow data from wherever it can. And so, for example, the hash map from symbol names to symbol IDs borrows data from the original input files. So that's what the tick data lifetime is here. It's saying that data is borrowed from the input file. And in order to make this actually work, scoped threads are super useful. So I love using scoped threads. Wild actually doesn't use scoped threads per se. It uses Rayon scoped tasks, which allow it to reuse the threads in the thread pool. But the idea is roughly the same. So if you haven't come across scoped threads, I've got a small example here. So the idea is we read some inputs into something, maybe that's a vector or something like that, and then we start a scope. And within that scope, we're free to borrow inputs. And within that scope, we can spawn threads. And so we split the input up into chunks, and then we spawn a thread for each of those chunks to process that chunk. And this allows us to borrow data across threads. So Wild makes extensive use of this via Rayon scoped threads. I've tried as much as possible to avoid heap allocations. And early on in the development of Wild, one of the ways that I avoided heap allocations was by using things like smallvec. But this turned out to have a bit of a cost that I hadn't really thought about, which was if you've got a lot of something and each of them might have, sorry, I should step back a bit. Smallvec lets you specify a size below which you won't have a heap allocation. So you can say, I don't expect to have more than 2 elements generally in a particular vector, but I might have more occasionally. And so as long as you have 2 or less elements, then it won't do a heap allocation. But if you, in the rare case where you do need more than 2, it will then do a heap allocation. So that the cost of this is, however, so it avoids the heap allocation, but the cost is when you go to drop all of these structures that have this optional heap allocation, you've got to check to see if the heap allocation actually happened. And so what I saw was that drop was showing up in the profiles, and that was just because it was having to go through thousands or millions of these structures, checking to see if they had a heap allocation that needed to be freed. So I've now moved away from this, and I try to avoid doing that wherever possible. In order to make sure that I'm not doing it, I implement copy for my types, because you can't implement copy and drop at the same time. That way I can know that I'm not accidentally implementing drop. So I try as much as possible to use vectors rather than hash maps. So wherever I have a sequential ID for something, or can generate a sequential ID for something, then I'll do that rather than using hash maps, because indexing into a vector is often significantly faster. So for example, when I'm building information about the symbols, I start by finding out how many symbols each object defines in its symbol table. So these are symbols that it defines and symbols that are undefined for that object. I then tally up the total number of symbols across all object files and allocate a single vector that's big enough to hold them all. And then I split that space in that vector, which is currently uninitialized. So I've got a large amount of uninitialized memory. I split that up into chunks, where each chunk holds enough to store the symbols for a group of objects that I'm processing. And then each of those groups is then processed by separate threads. So I can initialize the vector in parallel from multiple threads. Once I'm finished initializing all of them, I do a bit of a check to make sure I've done that correctly in order to keep things safe, before I then have access to the full vector that is now initialized. So I moved that has a little bit of unsafe code in it, so I moved that out into a separate crate called sharded vec writer. So I try as much as possible to avoid locking. It's very tempting when you're writing multi-threaded programs to have some shared mutable state that you just wrap in a mutex and then access from multiple threads. But whenever I've done anything like this, it often ends up being slower. And so as much as possible, I try to restructure the code in a way so that each thread has exclusive access to whatever it's working on. Sometimes this means the code is structured a bit differently, but it usually ends up being faster. So moving on to benchmarks. So this is showing a benchmark of the wild linker linking Rust C driver, which is where most of the code for the Rust compiler lives. I've excluded GNU-LD from the chart because it takes so long that it would mess up the scaling of the axis of the chart. But we can see on the right that we've got GNU-LD taking more than 21 seconds. LLD takes 1.6 seconds, mold takes 840 milliseconds, and wild is currently at 571 milliseconds. So we're doing reasonably well on this benchmark. We're a little bit faster than mold. If we link with debug info, then all the linkers get a little bit slower, and we're now a bit closer to mold. Still have a slight lead, but not much. If we try linking the C compiler, Clang, without debug info, then a similar sort of story, although both mold and wild have a reasonably sizable lead over LLD. I'm not quite sure why LLD is a bit slower there. However, and so keep in mind looking at those times, like we're less than 300 milliseconds for linking Clang without debug info. Debug info, it turns out, is really big and often really expensive. So when we pull in debug info for Clang, we've now gone from less than 300 milliseconds up to more than 18 seconds. So we're paying a really large cost for having debug info. So my advice, if you want fast builds, if you don't use a debugger, then maybe consider turning off debug info most of the time. That's what I do with a lot of my projects. It's not quite as bad with Rust as it is with C++, and I suspect the reason it's so high here is because there's a lot of repeated debug info from all of the headers that come from C++, because of the way C++ compiles code with everything being in headers, and those headers are repeated every time they're included. You get lots of duplicate debug info. I do have some plans for ways in which I might be able to speed this up, and most of it comes back to speeding up string merging, which is used a lot by debug info. So I mentioned before that I'd come back to this shutdown time that we're spending here. So what's happening here is this is where we're unmapping all of the input files that we've accessed. And it's tempting to think that we could fix this by just, well, we're about to shut down, so let's just leak the memory. Let's just exit. And it turns out this doesn't actually help. So I did an experiment where I just directly called the exit syscall here. So it didn't go through any shutdown at all, not even libc shutdown. And it didn't actually help. And the reason is that the kernel still needs to clean up these resources anyway. And so it just shifts where the time occurs. Similarly, doing it from multi-threads doesn't help because unmapping memory acquires a kernel lock, and so it doesn't help. There is one optimization that can help here, and that's something that mold does, which is when it starts up, it forks the process. So forking a process is where you take your process, and now you've got two processes that are doing the same thing, but you can do, well, two processes that start out the same and can then diverge and do different things. So when mold forks, the parent process then just sits and waits for the child process to do its work. The child process does all of the linking, and once the child process finishes linking, it signals to the parent that it's done. At that point, the parent can detach from the child and exit, at which point your build process can continue, leaving the child process to exit in the background, and it doesn't matter how long it takes to exit because it can just shut down in its own time. So I haven't yet done this optimization for Wild, but I will probably do it at some point. So another optimization, well, it might be an optimization. I have the theory that it could be, but I haven't yet tried it, is to try doing reads directly. So for copying data from the input files to the output files, I currently use memcopy. And where that data that I'm copying is data that I haven't yet accessed, that memcopy will be causing page faults because it needs to actually map the pages into the address space. The mapping happens lazily, and so we haven't yet accessed those pages yet. And so that's causing page faults to get the memory into our address space. And then we pay again when we shut down because we've got to unmap all of those pages. So my idea of using read is that the kernel is doing the memcopy for us, and it doesn't require any updates to our processor's address space because it's just probably copying from cache. So if the kernel has that data somewhere in cache, it can copy directly from cache into our output file. So I have a theory this might be faster. If I'm just using read, I suspect maybe it wouldn't be because there'll be overhead from all the system calls. However, the idea here is that I would then batch those read system calls using something like IOU ring, which is a relatively new API in the Linux kernel that lets you batch system calls. So fairly soon, I'm intending to start work on incremental linking. So the idea of incremental linking is it wouldn't be bit for bit identical to what you would get normally. And it's not something you would use for release builds. It's something used for development. And so what I would do would be I would leave space in each output section for future growth, or possibly for each input section, and then also write layout information to disk so that when we rerun, we know what happened before and we can update it. So when the linker is re-invoked to do an incremental link, we would first of all check to see which object files have changed. And then within the object files that have changed, we check to see which sections have changed. And if there were sections that we loaded before, we would update those sections. Possibly that would require pulling in new sections that we didn't pull in before. And some of the sections may not fit. So if a section doesn't fit because you've added some extra code and it's grown, then we would need to put that section in a new location in the output. If that's the case, we would then need to fix up references to symbols in that section. So that means that we need to know where everything came from. So we'll need a reverse index we need to have an index of what references what, so that we can fix up those references. So to store all of this on disk, my plan would be not to use serialization and deserialization, but rather have the same on-disk format as in memory. So this would allow lazy loading it would allow me to mmap the state files, which means if there are parts of that state that I don't need for the incremental link that we're currently doing, then we would never need to load those off the disk. This, however, would mean that we can't store references in any of that state, and so wherever we're currently using references, we would need to switch to storing indexes. But I don't think that should be a problematic change. So an alternative that I've considered is to keep the linker in memory. So this would mean that we wouldn't need to write state to disk and read it back. However, it would require a somewhat different workflow. So it would be something a bit more like cargo watch or bacon, where you're running a command and it's watching for changes and then rerunning a test or something like that. And so the link would remain running as long as that command was active, and then when you Control-C or quit out of cargo watch or bacon, it would shut down the linker. So that's a bit of a different workflow. It's possible I may do both, we'll have to see. So there are some overheads of incremental linking. So as I mentioned, there's the extra space that we need to allow for sections to grow. There's reading and writing the state that we need to track on disk. And there's also building that reverse index. So we need a reverse index for all references. But I'm hoping that those overheads are significantly outweighed by the benefits that come from not having to redo a lot of the work that linkers do. And they do quite a bit of work. So once I've finished incremental linking, I'm excited to have a try at doing hot code reloading. So the idea of hot code reloading is that we would be updating your program while it's running. This is definitely living dangerously, and there's definitely scope for things to go wrong here. It's something that is ideal for experimentation where you're building a stateful app and you don't want to have to get back to the same state in your app each time you're making a change. So for example, in game development, you might be wanting to make changes and then see what effect those changes have on your running code while it's running. There are some caveats. So for example, if you change your types, such as adding a field to a struct, then you would certainly need a full reload. And it would be nice if the compiler could tell us that types have changed so that we can signal to the user that a full reload is required. Linux's file locking gets in the way a little bit of hot code reloading. So it'd be nice if we could just edit the file on disk and have those changes show up in the running executable. But while a file is running, Linux locks the file and you can't open it for write. Similarly, if you've got it open for write, you can't execute it. Interestingly, Linux doesn't do this for shared objects. So you can edit a shared object while it's running and Linux will just ignore that. So one way we could circumvent this is just to put all your code in a shared object and then edit that. But I'm actually possibly more tempted just to implement my own loader, which would kind of do what Linux does when it loads an executable, but would do it all ourselves by mapping the file and then using other system calls to make the memory executable as appropriate. Because if we do a loader ourselves, then we can bypass, Linux is not aware that it's running the executable and it won't have locked it. Another caveat is that if you have data that you change in your program and that data is now bigger and needs to be moved to a new location, then any references that the running code made to that data may now be stale because you've taken references to where it was before. So there are caveats where you may need to do a reload. So my approach to testing the linker mostly comes down to a bunch of small programs which are written in C, assembly, and Rust. So I compile these programs, I then link them with the system linker, GNU-LD, and I link them again with wild, and I make sure that both versions exit correctly with the correct exit code. And that worked reasonably well, but it did result in me spending a lot of time stepping through both versions in a debugger. A replay debugger was really useful for this, by the way. A replay debugger lets you step backwards, which is great. You can run the program to the point where it goes wrong and then step backwards. But it was still very, very time consuming. And so more recently, I've implemented a tool that I called linkerdiff, which lets me diff to binary executables or shared objects. And it does so in a way that is tolerant of layout differences. So when it's analyzing the code, it looks at what your code is referencing and doesn't worry about the absolute values in there. So here we can see some output from linkerdiff. And so it's got several instructions that are the same in all versions of the output. So here it's a shared object that we're diffing here. But then we've got an instruction that is different. And we've got 3 lines there in the middle. One for wild, one for GNU-LD, and one for LLD. And we can see that GNU-LD and LLD both had a move instruction there, whereas wild had an LEA instruction. Also on the right-hand side, you can see that GNU-LD and LLD both had dynamic relocations associated with this, whereas wild didn't, which means wild was directly accessing this variable. So this was a bug that I had in wild at one point. Either that or it was something I introduced deliberately. But so one way, when we're debugging this kind of problem, it can be useful to look at the original relocation in the original object file. And the way that linkerdiff does this is wild generates a layout file when it runs, which linkerdiff can then use to work out where this function came from in the original input files. And importantly here we can see that the relocation that was in the original input file is a rex.pcrelex, which don't worry about what that means, but it's useful when you're writing linkers to be able to see that relocation and work out why your code did the wrong thing with it. So another thing that's useful is to be able to get debugging traces from the linker itself. So the way that I do that is I use the tracing crate, and I log the tracing messages into a binary file that I create. And in that file, each tracing message is associated with a particular address in the output file. And so linkerdiff can then, when linkerdiff encounters a difference in the output file, it can look at all of the bytes associated with that instruction and look for any log messages associated with those bytes. And so what we're seeing here is that linker diff looked at the bytes for that LEA instruction on the first line there, and it found a trace instruction associated with that, and it's displayed that trace line. So in the trace line, we can see that Wild applied a relaxation, which is a kind of optimization, and that relaxation was mov indirect to LEA. And so that's where it converted the move instruction into an LEA instruction, which it shouldn't have done. And there's a couple of values that it's printed that are associated with that can help for debugging. So thank you for listening about Wild. I've got a couple of resources up here. There's the repository and also my blog where I posted a bunch of articles related to linkers and related to Wild. I'd also like to thank all of my GitHub sponsors for helping make it possible for me to work on this kind of stuff rather than going and getting a real job. Thank you.